Let's get started. Last time we talked about RL/control learning through interaction controller. Or a policy. So this is kind of the learner, the agent, whatever you want to call it. Maybe a learner agent. It sends actions to its environment, which is the MVP. And as a response, the MVP is sending back a reward and the next state, or sampled from the underlying transition kernel. And the learner's goal is to get better at this in terms of collecting more reward. That's kind of generally the problem. But that's just like one way of phrasing the problem. So what is the learner's goal? It's generally getting better. So getting better in terms of what? And you can have multiple answers to this. One of the answers is that you want to get better at just collecting more reward as you go. Collect as much reward as possible, despite the fact that the learner doesn't yet know the system. That's one of the goals. The other goal, and that could be multiple goals, multiple others, but these are the most basic two ones, the two most basic ones. The other goal could be to kind of figure it out. Figure out what? Figure out that in the future, if I need to control the system, how would I do it? And do that as quickly as possible. So that's the goal of finding a near optimal policy as quickly as possible. Find a good policy or near optimal policy. So good just means that it's almost as good as the optimal policy. Either you have a fixed budget of interactions with this environment, and then by the end of that interaction, you want to get a good policy, or maybe you're giving a target that, okay, I need a policy that's epsilon optimal, and you're being asked like, okay, go as long as you need to collect the information and stop as soon as possible. You can guarantee that you have met the accuracy requirement. So there are these two versions. So this second goal has two subversions. And now you might be wondering about like, okay, like are these really different? Are these two problems really different? What do you think? So the first, we told the learner, collect as much reward as possible. The second one, we told the learner, find a good policy. Is it possible that you can have a learner that is good on one of these objectives and bad on the other, vice versa? Let's think. Oh, yeah. I think your thinking is absolutely on the right track. So a lot of times when you're thinking about problems like this, we should first simplify things. The simplest setting where this question can be asked in a meaningful way is the multi-arm bandit. You just have one state. And there, as you were saying, maybe there could be a strategy of like just pulling all the arms until you know which arm is the best. And pulling all the arms until you know which arm is the best is a horrible strategy in collecting reward, because you keep pulling the bad arms, right? So in that setting, but it's maybe a reasonable strategy for finding out which arm is optimal, right? So the second goal doesn't regard the rewards. An agent trying to meet this second goal doesn't need to worry about how much reward it's going to collect. It can use strategies which are very wasteful in collecting reward. And so maybe it's possible that you can have a learner which is good at this goal, and it's pretty horrible at this goal. It's not a proof, but it's kind of like a hand-wavy argument that you can imagine that if you're designing an algorithm just to meet this goal, then you definitely don't have to worry about the rewards that you're collecting. So you might be trying something that doesn't look immediately good, but maybe it leads to information that you really need in order to decide what would be a good strategy to do. So in a more complex scenario, when you have you're in an MDP or whatnot, it might be that you need to go to, if you need a policy which is good at every place, then you need to go to the bad places, the states where you can't collect much reward. But if someone was demanding that you need to have a policy which is good everywhere, then you have to do that. So that's a very different goal than having the goal of collecting as much reward as possible, because the agent that is tasked with the goal of collecting as much reward as possible doesn't need to visit those bad places, right? So you can imagine you got into a new town and you're exploring restaurants, and you're given the task of finding the best restaurant of all types at all districts. Then you have to be exhaustively looking at all types of restaurants, even those which are not too rewarding for you because you don't kind of like, I don't know, Hungarian food. Like you hate Hungarian food, but you still have to try all the Hungarian restaurants because you were told that you need to know which Hungarian restaurant is the best in town, right? So if you need to satisfy a goal like this, that might be contradicting this goal. So in the other direction, is it also true that if you're designing an agent to satisfy this goal, then it may or may not be good at this goal? Yeah. But no, we're thinking about a strategy which is getting the highest possible reward, and we would want to, maybe there is an example where you have a strategy that gets a lot of reward, but which is not good at discovering a good policy. Right. So we go back to the restaurant example, for example, then the agent that worries about getting as much reward as possible is going to visit the restaurants that it already knows that, oh, I kind of like that kind of food, and it's not going to explore the restaurants of other types. which they would need to do if they were given a task that, like, no matter what restaurant you will be thrown at, like, you have to be able to say what would be the best food there. Okay, so we see that at least in some cases these two goals are not aligned with each other. So the algorithms might be different for the two goals. So the first one, that's what I call online learning. Okay, so this is bad. Maybe I shouldn't call these by any names, because a lot of people use online learning in a lot of different ways, and maybe when you're learning online with an interaction in this closed loop, then, well, that's already online learning. But yeah, I call this online learning because it's like you care about the online performance, or online, I don't know, like on the go reward optimization.
So for statement two, how the policy, like beyond than getting a good reward, is more like finding out what not. Like, what's bad and what not. So I keep trying to find the.
But for example, if you're in a bandit problem, then if you collect as much reward as possible, and then you look back of which actions you chose a lot, and create a policy based on that, based on the frequency of actions that you chose. If you have a policy that collects almost as much reward as the optimal policy, you're granted that the strategy that you derive this way is going to be near optimal strategy. So it's like not, you need a more complicated setting like an MDP setting. What did I write here? MDN. Like an MDP setting, in order to have a conflict between these goals. So very simple settings don't have this conflict. Or at least it seems that if you're satisfying the first goal, then you will have a way of satisfying the second goal. Does it make sense? Because you were saying that
The policy is only like not the option, and further and you like further develop like iterate your policy to make it better, then wouldn't we just like ranking the actions from like best to worst, and pretty much like just like finding what not to do, like
true. And you want to do that as quickly as possible. Sure. What does this imply?
Like well, you need not perfect policy to find the best action.
To satisfy this goal, you don't need to find a near optimal policy. No, it's just like we had this definition of absolute optimality. That's the definition you should be thinking about. That means that the value function of the policy is not much worse than by epsilon than the optimal values that you would get. Even for any state, it's about the states. There are no actions anymore because we fix the policy. So even for whatever state you can think about, and it could be a state that you would normally not visit, like if you are, like you have an initial state and like you kind of are just exploring the neighborhood of that, or you'll be reset to, like, maybe you're in an episodic problem, you started an initial state, then if you're tasked to collect as much reward as you can, you want to go this way, but there is a lot of reward. At these places, there are not much reward, you never go there. But if you're tasked to find out an optimal policy that is, or near optimal policy that is near optimal everywhere, then reluctantly you will need to go to these bad places that are not according to your taste, and still you need to, because you were given this task, right? Like maybe you're writing a book about the restaurants of the town, then you would have a task like this, because it's not about optimizing what is good for you, but it's about gathering knowledge about like what's good in general. Sure. Oh, I mean, right. Right. So the example is a little bit fishy in the sense that I started to make an assumption that we know a priori that we have some states that we are not going to find much reward for ourselves. So we know something about which states are rewarding, which states are not rewarding, which may not be the case. And in those cases, you may need to go to those bad places, to those states as well, because you're completely uninformed about things. But there is a difference between whether you're gonna just very quickly discard those places as bad places, because you very quickly discover that, well, in the Indian restaurants, I can get a lot of reward, but if I go to a Hungarian restaurant in North America, there is no way I'm going to get any reward. Very quickly you discover by trying a few. And you will not want to optimize for those places and find out, okay, like given the restriction that I really need to go to a Hungarian restaurant, which food would be the best?
Another way to place my that know that taking this action off, but the other actions you have just less confidence on how optimal it is. I mean, how less optimal it is.
Okay.
So in that case, what the policy is so optimal, because like for a high confidence, you already found the best action. But other actions have a low confidence, big confidence.
Okay. I'm not sure what you're trying to say with this. Where are you getting? You're trying to make a point about? Is? So for that, we just have a definition, right? The a policy pi is optimal if its value function matches the optimal values at all states. So there is no change to this definition. And we said that pi is epsilon optimal if it collects almost as much reward as following an optimal policy would at all states. It's kind of like uniformity over the states. That's kind of baked into its definitions. Maybe you're talking about that, okay, you only want it for one state or something.
You explore one, you're confident this action that was this state is best, but the rest of the states you really explore like sparing, and you're unsure.
And you can be unsure about the exact things what to do there because you just discarded them as bad anyways. Yeah, you can do that if you want to collect as much reward as possible, but you can't afford to do that if you were taught that you need to discover what's optimal to do at every state. Right. Okay. So this whole thing when you are interacting, this is really called online learning. But I also said the last time this is like online access when you have a trajectory and like you don't have resets and whatnot. And so the last time we talked about some ways of getting good policies, and that was kind of talking about this second goal. So finding a good policy. And we were talking about that an interaction model that the learner can not only send an action to the environment, but it's kind of almost have a simulator of the environment or something. It can say that, hey, environment, at this state, if I would take this action, what would be the result? What would be the next state? What would be the reward? Sampled from the transition kernel. And it has this richer interface. That was the global access interface. And under that interface, I told you that if you just, at every state, you ask for every action, you build a model, you solve that model, you collect enough samples, this is going to give you, and you solve the resulting model for the best policy for that empirical model, then this is going to give you a near optimal policy, or as good a policy as you can get with finitely many samples. And so that's a simple setting. But if you go to the online access setting, then you have to immediately distinguish between these two goals. And then there's a question of, okay, which goal do you want to work for? And it depends on the papers. It really depends on what you think is more important. It's actually very, very rare, I think, that people would be seriously thinking about finding a policy which is good everywhere. Even in the most distant parts of the world and the corner of the universe, it's like, how would you do that? Like, that's not really reasonable. So a lot of times you relax this goal and you're saying, I don't want a policy that is near optimal everywhere. I want a policy which is good from this state, single state, or a distribution over the states. It's localized, okay? And so there is the global version of this goal, which is kind of hardish, and there is a local version. If you have the local version, that's a much closer friend to collecting as much reward as possible. You might be wondering about, okay, if you have the online access model only, you can only have a single trajectory of interaction, then how can you deal with this local problem? In general, you can't, because maybe someone asks you, okay, at this state, what is the best to do? You start at that state, you're lucky. But you make a step, and you stepped away, and there is no way of getting back. Then you're stuck, right? No algorithm can do anything clever. So in order to deal with that, you really have to have something else than just this online access model. You have to have something like a reset. We talked about what the reset is. So in this case, you may need to have a reset. If you have a reset, then it's like almost like an episodic problem. So you might as well think about, okay, I have an episodic problem, and I can reset to the initial state. And I just want to be as good as possible from that initial state. And a lot of problems that people consider, well, okay. There are a lot of problems that look like episodic problems. There are more problems that look like non-episodic problems, where you have all these difficulties that you have seen one state, but maybe you will never see it again. Okay. So the last time we talked about this global access, we talked about mainly the second goal, globally good optimal policy. We had a very simple strategy to deal with that. We talked a little bit about also Q-learning. And we discussed one specific thing, which is that what makes these problems, these learning problems, very different from the planning problems that we talked about before, which is that you're given the description of the MDP, is that you might need to explore, right? And so especially if you only have online access, no global access, then there is a big need for exploration. So getting to a state to see what's the best there is highly non-trivial. And you are expected to be able to do that before you learn how to act in the MVP, maybe. So the question is whether this is a manageable process, this is a manageable learning problem, or not a manageable learning problem. By manageable learning problem, you mean that, okay, maybe you have so many states, so many actions, so the cost of learning shouldn't be more than proportional in the number of states and actions. All right. So exploration. In the bandit section, they learned about a few ways of exploring things, exploring the actions, the arms. What were these? Do you remember some of these strategies? Okay. So Shivam knows epsilon greedy. Thank you. What was epsilon greedy doing in a bandit problem? Bandit problem, you have finitely many actions. You can choose one. You get the associated reward. It's like an MDP with a single state. And you try to maximize the total reward. What does epsilon greedy do? That's right. So I just repeat so that everyone hears it. Epsilon greedy computes based on the statistics that it collected for all the actions, which is the average reward for all the actions. What would be the best action at this stage, given the statistics we have, given the empirical means of the rewards for every action? You compute the one that gives you the highest empirical mean. That's your candidate to choose, and you want to choose it almost all the time. So you have this tuning parameter epsilon, and with probability 1 minus epsilon, you're choosing this action. We call this an exploitation step. And you, with probability epsilon, you uniformly at random choosing some other action. So that's epsilon greedy. Epsilon is probability parameter that controls how much exploration you want to do. Right. Yeah. Okay, so I think that you're talking about optimistic initialization, right? Good. Again, just to repeat what you said, you initialize the values high, and the idea is that that is a good idea there. The idea is that you need exploration when things go wrong with the good actions. When are things going wrong with a good action? The things are going wrong with a good action when you get unusual rewards back from the good actions. So you expect high rewards from good actions, but it's random. So due to the randomness, you pull the good action, you try the good action, and you might observe low rewards for it. You're just unlucky, and it has a positive probability of happening, and you don't want to be stuck when that happens. If you initialize high and you use these incremental algorithms to update the mean reward, what happens in this case is that, well, you initialize high, so it starts high, still high, even though it's going down. And when this is happening, then maybe, okay, the bad actions, if you initially think that they are better, you keep trying them, but eventually the statistics of that is going to correct itself, and it will go below the value that you assigned to good action because it was initialized high. If the good action value was not initialized high, but it was initialized 0 or something, or low, then you're coming from below, and the value that you assign to good action might actually be lower than the value that you're assigning to a bad action in this unlucky scenario. So you're trying to correct for this unlucky scenario in this heuristic way. This is the underlying idea. The good thing about this idea is that, yes, you really need to worry about the good actions receiving unusually low rewards, and that shouldn't stop the algorithm from keep using those actions indefinitely. So what is an alternative to optimistic initialization which also tries to do this? Yeah. Okay. How's upper confidence bonds? How does this work? Yeah, it's fine. There is.
Gives the upper bound probability that like that's what you get. That probability.
Yeah. Okay. So I rephrase a little bit and make it more precise, but that's kind of the idea. So the name is upper confidence bonds. And so the idea there is that you have these random rewards that you receive for an arm. And that gives you a confidence interval, right? So mean is just like one characterization of what's going on. But you will also have a standard deviation for the statistic and so on and so forth. So that is, it's better to characterize of the information that you received from that arm in the form of confidence intervals at various levels. So what's the meaning of a confidence interval? The meaning of a confidence interval is that it's an interval that you compute based on the data, such that if you would be repeating this experience, then a fixed portion of the time, which is the confidence level of the interval would actually contain the true mean. So it's kind of trying to capture the true mean, and it's guaranteed to do that with a given probability. Okay? And it's computed based on the data. And so in the third algorithm, the idea in the UCB algorithm is that when you look at an arm, you're not saying that, well, this is the mean of the arm, so this arm has the highest empirical mean, I should go with that. But you say, well, for every arm, I do have this confidence intervals. And so for this arm, this is the confidence. In the next arm, the confidence interval is like this, or something. So you look at the potential of the arms. Like, could this arm be the best? And then you choose the arm that could be the best. Meaning that the confidence interval, you trust the confidence interval, you say that, well, the mean can be anywhere in the confidence interval. It can be at the top of the confidence interval. That's the point of the confidence interval. It tells you where the mean could be. It could be at the highest point of the confidence interval. So you look at all the arms and you say, okay, what's the potential for this arm? But the potential is that the mean could be the highest, at the end, the highest end of the confidence interval. That's the value you assign to the arms, and then you choose the arm with the highest such value. Okay? And this is an instantiation of a more general principle, which is the principle of optimism in the face of uncertainty. So this is an algorithm design principle that is applicable not only to bandits, but to a wider area of sequential decision-making problems under uncertainty when you don't know the environment. It's a stochastic environment, and you want to do you want to do well. And the goal here is to collect as much reward as possible. Okay. So how is this? What does this principle say? This principle says that, well, you have possible models of how the environment is working. You collected some data. You can rule out some possible environments. So those lie outside of the feasible set of the environments. And for the remaining environments, you just choose the environment which looks the best, which gives you the highest value, and you compute how to act optimally in that environment, and you just follow that. So the picture in my head is like this. You have all possible models for the environment. It can be as simple as bandit models, as more complicated as MDPs, or even more complicated than that. So you have all these models. They are probabilistic models. They connect actions and observations. So given the actions and observations that you collected, you go on and then you rule out a bunch of models. And you have a set of remaining models. These are feasible at some confidence level. So these are the likely ones, in a way. And all the others, if you rule them out, you don't have to worry about that, because the probability that, given the data, the environment belongs to the set which is ruled out is low. And you don't worry about low probability events. Some low probability events need to be discarded sometimes. You can't worry about every low probability event, because then you're going to be, you're going to have a horrible time, because you worry about that the brick is going to fall on you, and you're going to slip and break your neck, and like you're just going to be too worried about everything. So you choose some confidence level, you discard some environments, and from the rest, you choose the one, it's usually at the corner in a way, the environment where the value is the highest. So for example, if you have value functions and you have some initial state distribution, maybe an episodic problem, you have some initial state, then the value of the initial state would be the highest. Then you just choose that environment. And you compute what's the optimal policy there, and you follow it. You collect more data, you repeat the process. Maybe you change the confidence level because you want to be increasingly confident as time goes by. You can do that in a principled way. And this is how generally designing the algorithms designed based on the optimism principle work. Why is this called the optimism principle? Because it looks at all the possible words or models that could exist. Okay, it's not stupid. It uses the data to discard the ones which are contradicting the data. From the remaining set, it looks and chooses the word that seems to give the best value, the highest. That's optimism, right? So that's the potential for that is potentially best that you could hope for. So that's why it's called optimism. By the way, there is a psychologist at UCL London who wrote a book about the optimism bias in humans and animals. So it happens that humans and animals, when they are learning, kind of exhibit an optimism bias. So maybe biology knows something. It's kind of funny because this optimism principle has been discovered quite independently of this research. So eventually, okay, everything maybe comes together. It's kind of like a nice story. So the name of the book is Optimism Bias. And I think that the author's name is Charlotte. And it's just a power boost, but summarizes the research on the psychology of this. Kind of find it amusing that these things can be converged. All right. So when you need to explore, you have all these choices, and there are other choices that people are recommending. Randomizing something that's epsilon greedy. There are maybe other ways of randomizing things. And then there is this optimism. So when it comes to MDPs, we have the same questions, like how should we explore? And you can try any of these strategies. You can implement the optimism bias. It also leads to some specific algorithm that is relatively easy to derive and write if you have, let's say, an episodic MDP. And you can test them, and you can derive, theorems about them, and then people do that. But instead of doing that, I just wanted to show you some videos, and then we can talk about what's going on the videos. And I know that, yeah, we don't have much time, but hopefully it's going to be enough to see some fun videos. And then the next time we are going to discuss a little bit more about the background of this, of all of these. Okay. All right. So, well, you can, let's see it here. This is really weird. Okay. So this is about cart pose swing up. It's a physical system, but it's done in simulation. Come on. So what's the physical system? It's like there is something hanging in on the rod, and it can move left and right, and it has a free angle, and you have to swing it up. We'll see it from the videos. And different algorithms are applied to this. The algorithms are kind of general purpose. They don't really know what they are controlling. The action space is like kicking this thing left, kicking this thing right. And OK, you will see it in a second. So we start with epsilon greedy, create some tension. So you can see that it's kicking it, and like this rod is flexibly moving in the bottom. The task would be to do some jerky motion so that it swings up and it stabilizes at the top. And if you're clever enough, you can write a controller for this. It's not trivial to do that. So it's kind of an interesting control problem as well. And now you see that there is something that, so my colleague Ian Osborne at DeepMind made this video. So there are exploration methods which are kind of following this optimism principle. He calls them deep exploration because they are kind of like deeply thinking about the value of exploration. And deep learning is very popular anyways. It's a little bit cheeky, but it's OK. And you see that, you could see that epsilon greedy had quite a bit of trouble. Let's see it again. that 100 episodes, epsilon greedy is kind of pushing left and right. 500 episodes. It's not a super complicated system. It's like a nice visualization, but if you think about what the state is, it's like where this thing is on the rod, and what the angle is, and maybe what the velocity is at. So it's like a 4-dimensional state space. And the reward is like, if you're upright, then you are rewarded, and otherwise, it sucks, no reward.
The goal stays like very far.
Right. Unless it kind of cleverly figures out that that wouldn't be clever. So by chance figuring out wouldn't be. So epsilon greedy is kind of just seeing no signal in this case. It sees that not good, not good, not good. Let's try to add exploration to not good. Well, it's not going to work. It's not going to do much. Whereas these other exploration schemes are a little bit more conscious about it. The question is, what is the heuristic reward that you're going to use, right? Like, are you going to design a heuristic reward by hand? The whole goal was to have something that works out of box, no matter what the system is going to be, right? So yes, we can fake it, but it's, yeah, we want to have algorithms that work under general settings, like as general as possible. So we want as little prior knowledge as possible. All right. I think that's it for today. This was kind of the teaser of, and then next time we're going to talk about what was happening here in these experiments. And yeah, exciting stuff coming up.